Hello, and welcome to Aggressive Physics. Today is day 36, and what we're going to look at is finalizing our discussion of equilibrium. And what we'll do is solve a problem that deals with an object being supported by two ropes, but not directly in the center, and therefore the angles are going to be slightly different. Now, if the angles are different, we're going to have to treat each end of the rope, or each strand of the rope, with a unique name. And that's because the values are not going to be the same. The fancy word for the force on a rope is tension. So we'll often use T to represent the variable for the forces on a rope. So the tension in the right strand and the tension in the left strand. For the problems that deal with the same angle on each side, we could just use one variable, typically T. A lot of times you'll also use A or B. But in this case, you'll have to use different variables. So if you're using T for tension, you'll have to denote each tension separately. So one would have to be T1 and the other would have to be T2. You could also use A and B. So one side would be A and the other side would be B. But remember, anytime you're dealing with a vector problem that involves equilibrium, you need to force the vectors to become perpendicular. So you're going to have to resolve that hypotenuse into its components. You're going to have to break legs, but you don't even know the size of the original vector. So you have to use the term or the variable that you decided instead of the number. Before, we used 100 newtons at 30 degrees. Well, you would type in 100 cosine 30 and 100 sine 30 for x and y. In this case, you have to leave the T, the A, or the B. And you'd have to write, if we're using T, it might be T1 cosine 30, T1 sine 30, and then T2 cosine 40, and T2 sine 40. If they were the same angle, you just use one letter. If you have different angles, you have to use unique letters for each strand. Now, of course, we're keeping these problems as simple as we can. We're dealing with two strands of rope. Real-world problems might have three dimensions, might have more than two or three strands. Let's say we're trying to keep a tent up, and more importantly, let's say a circus tent, a big top tent. You have multiple forces acting on that canvas. You have a huge amount of total weight acting down, but you're distributing that weight over all the different poles that are supporting the tent itself. So that is a really complex problem in three dimensions, and you'll notice that if you have a tent being erected, you'll have the tent poles at different angles, you'll have guy ropes coming down, and it's going to be a much more complex problem. Now, you could, of course, do that with the same concepts we're dealing with here, but you have many more forces. So what I like to do is start with problems that have the minimal number of variables and then increase the difficulty. So we'll ramp it up as we go. But for today, let's look at a simple problem where we have an object that is being supported by two ropes, but the ropes are at different angles. So the tension in each rope is unique. Now this can be, as I said, related to real-world problems and real-world applications, putting up a tent, hanging a sign, putting out your clothes on a clothesline, even if there is a tree limb that happens to hit a high tension wire that's carrying electricity. Outside my house a few years ago, there was a tree branch resting on the electrical lines after a storm, and it was important that the electric company came and took that tree down, or that tree limb down, before it broke the line. Now, because it was under high tension, it had less room for the tree to actually add extra weight to it before it snapped. So it was time dependent. Of course, it was extremely dangerous because of the high voltage electrical lines. So those are all things. Equilibrium, although it seems like an abstract concept in class, actually applies to real-world applications quite well. So let's solve that problem now, and we'll move on to more complex problems from there. This concludes our discussion of equilibrium, and we'll we'll move on to another topic starting tomorrow. Thank you. All right, here's another example of an equilibrium problem where we have a bear bag that is hanging from a rope, but the bear bag is not hanging in the center, and it produces two different angles. And from the wording of the problem, we have a 40-degree angle on the left and a 27-degree angle on the right. The bear bag itself is 25 pounds, which is 111.25 newtons. Now we could leave that in pounds if we wanted to and just find the value in pounds, but I'd like to stick to the metric unit as a little foreshadowing for our next topic, which is going to be forces. Now, like any mathematical vector problem, we're going to want to break the legs, resolve them into components, and get our x's and y's. Cosine and sine for each. However, since the angle's different, we need different unique names for each strand. So I'm going to just call this A and B. We can call it T1 and T2, but I think A and B will just be how we'll solve this one. This component is A cos 40, A sine 40, B cos 27, B sine 27. Now, when we set this up, we want to sum up the x's and set it equal to 0. So it'll be B cos 27 minus A cos 40 equals 0. And we'll sum up the y's and set it equal to 0. So it'll be A sine 40 plus B sine 27 minus 111.25 newtons equals 0. And what we have are two equations, and we have two unknowns. Now, typically, since we have less terms in the x, we'll simplify it. And the way I think we'll do that is we'll solve for b. Now, the way we're going to do that, I'll do that here. If I want to get b by itself, I would subtract the a cosine 40 term, and then divide both sides by cos 27. So b equals a cosine 40 over cosine 27. Then I'm going to take what b equals and substitute it into the second equation. So we have a sine 40 plus, and here's where we're going to simplify, a cos 40 over cos 27, and that replaced the b, times sine 27, and that's going to equal 111.25. Well, if we look, a is now our only unknown. And this becomes slightly difficult in terms of the algebra. However, we have a sine 40 plus a cosine 40, and remember, sine over cosine is tangent, so tangent 27 equals 111.25. Now, although they're not whole numbers, it's fractions and it's decimals, sine and cosine are just numbers. So I'm going to combine these two terms first and then add it to the sine of 40. So I'm going to do cosine of 40 times the tangent of 27. I'm going to get a number, 0.39. So a times 0.39 here. And then I'm going to do a times the sine of 40. Sine of 40 is 0.643. And all I have to do is add those two terms together. So if I go back to 0.390319139, and I add it to the answer, I get, of course, I put too many decimal places. So let me do that again. Cos 40 times tangent of 27. Cos 40 times tangent 27. That equals 0.39 plus sine of 40. I get 1.033a equals 111.25. Divide by both sides by 1.033. So 111.25 divided by answer. I get 107. A is 107.7 newtons. And use n for the units for newtons. Now, of course, we have two vectors. So A up here, 107.7. In order to get B, I need to substitute it back into the first equation. So B cos 27 minus 107.7 newtons cos 40 equals 0. So that's back into my start equation. Now, I'm going to take the 107.7, which is still in my calculator, times cos 40. I'm going to bring that over so it's positive, and then I'm going to divide by the cosine of 27. And B should be 92.6 newtons. 92.6 newtons. So we have 107.7 on one side and 92.6 on the other. And that's how we solve for vector equilibrium problems that have two